Okay, so today we are going to start the new topic in organic. It is phenyl amine and its molecular formula is C6H5OH. Sorry. Phenol is C6H5OH, it's C6H5NH2. So here in phenylamine, NH2 group is bonded to benzene ring. So its structure would be like this. A benzene ring, and over here one NH2 group, and molecular formula I have written above. Okay, so first we are going to discuss about its preparation, that how can we prepare it. So we can start it from benzene. First nitrobenzene is prepared so we know this reaction, we studied it in benzene. So here we have a benzene. Benzene is actually allowed to react with concentrated nitric acid. And for this reaction, we need a catalyst which is concentrated sulfuric acid, and 25 to 65 Celsius temperature is maintained by heating. So as a result, electrophilic substitution of a benzene occur, and a nitro group which behaves as an electrophile substitute the hydrogen forming HNO2, and the hydrogen releases reacts with the OH to form water. We already did this reaction, I hope everyone knows. So
Yes.
we got a nitrobenzene, right?
Yes.
And we have to make phenylamine. So this on producing nitrobenzene phenylamine is formed. So in this reduction, the reducing agent that we need is tin metal and concentrated hydrochloric acid. Then condition, heating under reflux. So we know when we use a reducing agent, we in the equation we show it by atomic hydrogens. So that is a nitrobenzene. Here I will show you 6 hydrogens, and the condition is 10 and concentrated HCl as the catalyst and reflux. So the NO2 group on reduction converts into amine group NH2, and 2 moles of water are formed. It is C6H5NO2 and it is C6H5NH2 nitrobenzene, and here this is phenylamine. Okay, but as you have seen that there is a acidic conditions in which NH2 group is formed. So due to acidic conditions, phenylamine formed accepts hydrogen ion to form phenyl ammonium ion. And this is phenylammonium ion because amine is, we know, basic, right? So and base accepts the hydrogen ion, so Nitrogen have a lone pair, and due to which it accepts hydrogen. Okay, is this understandable to all of you? So what we do, so at the end of reaction, sodium hydroxide, or we can use any other alkali, is added to form phenylamine again. So that's what happened. Here we have a
Sir, the
yes.
hydrogen will uh, join with NH3 from water, right?
No, not from NH3. Let me explain you. See,
Okay.
we have what we want to form this thing, right?
Okay.
And
Yeah.
we are preparing this thing from this, and for that we use this as a catalyst, right?
Yeah.
So
Yeah.
it's an amine, and amine have a nitrogen, right? And
Yes.
nitrogen have a lone pair, and it is acid. Acid produces excess hydrogen ions. So this
Oh,
amine, phenylamine, is actually producing or forming in acidic medium. So what it will do, it accepts this hydrogen ion and turns into this thing.
okay.
So
So
instead,
hydrogen from HCl will combine.
yeah, from the acid.
So, sir, then we will have chlorine ions left.
Yeah, obviously, chloride ions are the spectator ions.
Yeah. Okay.
So what will happen then if we add the alkali? So alkali, when we add the alkali, alkali gives us hydroxide ion. So this releases the hydrogen ion to neutralize the alkali, and water is formed, and again we got this. So this is what happened. So that's why we are adding alkali at the end to restore phenylamine. So
So, so that's how we will get NH2 at the end.
yeah, due to the
Okay,
acidic
sir.
medium, we are not getting NH2 initially, we are getting its salt.
Yeah.
So to make the phenylamine again from its ammonium ion, we will add alkali, and on adding alkali, there are excess hydroxide ions, and to neutralize those hydroxide ions, it releases the H positive, forming phenylamine again, and the alkali neutralizes the acid.
So, sir, it's two steps, right?
Yeah, but if examiner asks you, this thing is all for reasoning. If examiner asks you, otherwise, if examiner just write this thing and you have to make the product, so we always make the product. We do not show this one.
Okay. The first step is how a phenylamine is formed.
Yeah, but this is formation of phenylamine is two-step from benzene. In this way, we will get a nitrobenzene, and on reducing that nitrobenzene, we will get phenylamine.
Okay, sir.
Okay,
Got it.
good. Yes, Yusuf and Hassan, if you guys have anything you want to ask, please. Or is this clear to all, both of you? Okay. Now, we have our reactions of phenylamine. So first let me explain, then you guys will note it down. See, in phenylamine, if you see, this nitrogen also have a lone pair as oxygen and phenol have. So it induces its lone pair to the benzene ring. So if the pair of electron is being introduced in the benzene pi ring and then the orbital of the nitrogen overlaps with the orbitals of the pi orbitals, p orbitals of the carbon. So as a result, now there is an enhanced or increased negative charge density in the benzene ring, and specifically on these positions, which we have discussed in phenol as well. So when phenylamine undergoes substitution, it will undergo electrophilic substitution, and that electrophilic substitution will occur at 2, 4, and 6 position in phenylamine.
Okay, sir.
Okay, so just note it down this quickly, and then we will do the reactions.
Sir, can you explain again how it's only 2, 4, 6? If only one p orbital of nitrogen
Yeah,
and one of carbon is overlapping.
sorry, can you repeat again?
Only one p orbital of nitrogen and carbon is overlapping, right?
Yeah,
So how does it form with 2, 4, or 6?
actually, that we discussed the same thing in the phenol. But if you recall, I didn't explain the whole thing because it is not the part of the syllabus. But let me explain you. For example, if it's a simple benzene, assume it's
Yeah.
a simple benzene. So in simple benzene, how many pi electrons are there? If it's
6.
6, agree? Okay.
Yeah.
Now have a look at the structure of benzene first, so it will be more understandable for. So this pi ring actually means that there are 6 electrons, right?
Yes.
Okay. Now think, if here we got an OH group, this oxygen have a one pair of electron, oh sorry, 2 pair of electron. Okay.
Mm.
Then, for example, we have a chlorine, it also have a pair of electrons. Then there is a nitrogen, it also have a pair of electron, right?
Yes.
So these pair of electrons will actually present in their one of the p orbital.
Yeah.
So
And that
this,
will overlap.
yeah, if this will overlap, so these pair of electrons will also delocalize into this system.
Yeah.
So now it means, due to the groups like this, which are electron donating in nature, will enhance the negative charge density over here, because initially
Yes.
there are 6 electrons, now there are more electrons. So
Yeah. It gained electron.
yeah, if the electrons are here, the electrons of the other atom or a group is delocalized in this ring, due to which the negative charge density increases over here. And as a result, it can able to gain the electrophile or attract the electrophile more readily, because the intensity of the negative charge is now higher.
Yeah.
Is this clear? Now, why it occurs
Yes,
on
sir.
4 and 6? The reason behind this is, for example, have a look over here. There is an electron donating group. Let me represent with the D. And here there are a pair of electrons. Basically, this information is not the part of the syllabus. So it's for your understanding that why we are saying that the electrophilic substitution occur at 2, 4, and 6. If it induces the electrons, so it will try to make another bond over here, right?
Yeah.
With the carbon. And if we look at this carbon have all the four bonds.
Yes.
So that's why if this will happen, and as a result, a bond will form, then what will happen? Any one of the neighbor carbon takes the electron of that carbon which is involved in pi bonding, and as a result, see, the pi system is disturbed.
Yeah.
Now see, where the negative charge is on right now.
On the carbon.
Which carbon?
Second carbon.
Second carbon. Now, if this pi bond moves over here, because we know that the pi, like it's a delocalized system, so the electrons are continuously moving, right?
Yeah.
So when this will happen, then pi bond comes over here, and this carbon got a negative charge.
Oh, okay. And that's the fourth one.
Yeah, and when this move over here, then see.
Then the sixth carbon will have it.
Yeah, then this sixth carbon have that pair of electron due to which it carries a negative charge. Now, if this charge is introduced over here, then this electron donating group's electrons, it takes the electrons back. And as a result, see, so the negative charge or a pair of electron in the ring is actually delocalized between 2, 4, and 6 position. So electrophile will
Sir,
attracted
if the
on.
form is the bond in the first one is formed from the on the second carbon, then can the positions be 1, 3, and 5?
Sorry, can you repeat again?
If the bond on the first step, if it's formed on the second carbon.
You are talking about this.
Yeah, this one.
If you are saying that it's bond over here like this.
Yeah, like this.
So now this is the first carbon, na?
Okay.
Well, the positions where the three, when the 3 and 5th carbon get substituted, it is when the electron withdrawing group is attached.
Okay, sir. Got it.
So what electron withdrawing groups will do? Electron withdrawing groups withdraws the electron from the pi system.
Yeah.
So
So it won't be in delocalized anymore.
Yeah,
right?
it actually withdraws the electrons from the pi system. So as a result, it induces a positive charge in the system. And then that positive charge actually going to circulate in these 3 positions only. So
yeah,
at that moment, on the same positions, the negative charge density decreases. So if the electrophile is coming in that case, then it would always be attracted to on these positions because the rest of the 3 positions have a positive charge.
Yeah. Okay.
Is this understandable?
Yeah, sir, I got it.
Okay. So that's what is the case with the phenol or with the phenylamine. Okay. So is everybody noted down till here? Yes, Yusuf and Hassan, if you guys have any query, please ask. Maham, if you find anything ambiguous, you can ask.
Okay, sir.
And as you guys finish noting it down, please let me know so we will continue.
Sir, I'm done.
Yes, Yusuf and Hassan? Yes, Yusuf and Hassan, are you guys done as well? Please give me a moment, please. Okay. Now, we have a first reaction with bromine. So, as phenylamine is more reactive than benzene, so obviously it will react more readily, and it also does not need any catalyst as benzene do, like anhydrous AlBr3 or AlCl3, and it will react at room temperature without any catalyst. So phenylamine reacts with bromine at room temperature only. So we have a NH2 group, and it reacts with 3 moles of bromine. As a result, bromine gets substituted and all 3, 2, 4, and 6 positions, and 3 moles of hydrogen bromide will form. Yeah, is this equation is clear to all of you? And during this reaction, the product over here formed.
Sir,
Yes.
in the reactants, there's only 2 hydrogens, and in the products, there's 5.
Hydrogens. Okay, you are missing one.
Yeah.
Maham. What is the what is the formula of this molecule?
Oh, okay, okay. They will be replaced. The bromine will replace them.
Yeah, the bromine are replacing those 3
Okay,
hydrogens.
okay. Yes, sir. I forgot.
So no problem. 2,4,6 tribromophenol, and here we are going to observe. There will be observation. Bromine is of orange color, so orange to colorless. Now we have a second reaction. Beside electrophilic reactions, bromine oh sorry, phenylamine are used for to prepare dyes. Dyes are the colors which are used in textiles, which are used to color, normally the clothing colors or clothing dyes are made from usually from phenylamine. So phenylamine is used to make dyes these dyes are called dyes. Okay. Now these dyes are also formed in a two-step reaction. These dyes are formed in two-step reaction. The first one is that is what we did in the preparation of phenol as well. That phenylamine, we allowed phenylamine to react with the nitrous acid or nitric 2 acid. So in the first step, phenyl reacts with nitrous acid. It is also called nitric 3 acid, and its formula is HNO3 to form diazonium salt. So basically, nitrous acid, I have discussed earlier as well, is an unstable acid. It is very unstable. We cannot store it. It absorbs the oxygen from the atmosphere and oxidizes to nitric acid, HNO3. So that's why we have to produce it in the test tube at the time of the reaction only. So we produce it in a real time at the moment where we need it. So produce in test tube at the time of reaction by mixing NaNO2 and sodium nitrite and hydrochloric acid. So when these two reacts in the test tube, nitrous acid, HNO2, and sodium chloride will form. So that is the first step in making of, if you recall, phenol as well. We call it nitrous acid, or it is also named as nitric 3 acid. Okay, is this clear? Now,
Yes, sir, clear.
okay, in the same test tube, what we will do, phenylamine is added. Now, phenylamine is added. To the test tube, and a diazonium ion or diazonium salt will produce. And if you recall, if we heat it with the water, nitrogen gas releases from the diazonium salt and it turns into phenol. So, but here we are not going to heat it because we do not preparing phenol, we are preparing a dye. So, and for this reaction, we need a temperature equals to or lower than 10 degrees Celsius. And for that, we used ice bath. So, this amine group on the benzene ring turns into this, and that's why it is called diazonium. And it's a diazonium ion, and if we attach a chloride, we call it diazonium chloride. And H2O will form as well.
Okay.
Its name will be benzene diazonium chloride, and it's a salt. And you can easily see its molecular formula is C6H5 N2 positive and Cl. Okay, so in first step, a diazonium ion is produced. Now, if you recall again, if we heat it with water, this diazonium chloride or diazonium ion, it will releases the nitrogen gas and OH group gets substituted over here, and phenol is formed. But now here, this, the diazonium ion, see, it's a positive ion. So positive ion is an electrophile or a nucleophile?
Electrophile.
Electrophile. And we know that benzene will, and all the aromatic compounds, the compounds which have a benzene ring will undergo electrophilic substitution.
Yeah.
Right? So if there is a phenol, if I add phenol in it, so it will act as an electrophile for that phenol. And this diazonium ion will displaces the hydrogen and get substituted on the benzene ring of the phenol. And that compound over here formed is called azodie. And this reaction over here is called coupling reaction. Okay, so see, This is a positively charged ion, which means it's an electrophile, right?
Yes, sir.
And here we mix the phenol in alkaline condition. So see, for phenol, isn't it this thing act as an electrophile? Because it's a positively charged. So what will happen that it loses the chloride ion, and from the benzene ring a hydrogen ion is released, and that hydrogen ion which is actually displaced. So that hydrogen ion and the chloride ion joins to form HCl. And here, for example, as it's a bulkier group, so it may, uh, its substitution at carbon number 2 will be little difficult, or at 6 because of the OH group. Then that's why it is substituted over here on carbon number 4 of the phenol, and this is this highlighted part is basically called azo group, and this whole thing is a azo dye, which is orange in color, and the actual name of this whole molecule or this dye will be 4-hydroxy
Sir,
phenyl.
how did HCl form?
1 minute. Azobenzene. See, there is a chloride ion on the benzene diazonium chloride,
Yeah,
and the hydrogen ion which got substituted from the benzene ring. See, from here, it's substituted over here in this phenol ring, na?
Oh, okay.
So from here, there
Yeah,
must
the
be a
one on bottom.
hydrogen. Yeah, there must be a hydrogen which is substituted.
Yeah. So the nitrogen lone pair will bind with the carbon on the phenol.
No, basically, this will attack over here. The lone pairs are still available if you see, because both the nitrogens have a triple bond. There are no 4 bonds.
So the bond will break?
Yeah, the one bond, see, there is a triple bond over there. So one of the bond.
Yeah. Okay, sir.
Okay. Till here, is this clear?
Yes, sir, it's clear.
Okay. So if we talk about this reaction, as we see that diazonium have a positive charge, so we can write over here that diazonium ion behaves as an electrophile and gets substituted on another aryl compound. And when we say aryl compound, it means any compound which have a benzene ring. Okay. So not with phenol only. If are other benzene containing compounds, if you can see over here, so they all forms di. These all are di. See here, instead of benzene, instead of phenol, this group have a phenyl substituted amine, and this diazoniamine substituted over here to give you a yellow dye. In the same way, we have a 1-naphthol, and it reacts with the diazoniamine, reacts an electrophile with the 1-naphthol as well, and getting attached over here and forms a dye. So basically in these dyes, the pi bonding system extends. See, this is the whole pi bonding system. This is another pi bonding system. And here we have a pi bond. So due to this pi bond actually interconnects both the pi bonding systems. So the electrons over here will be extended to this ring and from this to back over here. So the delocalization will be extended like this. And that's due to this extended delocalization, these dyes becomes very stable. So they will not,
Okay.
the color will be very stable on the thing. They will not fade
So
off.
the bond will be strong?
Yeah, bond will be strong and the color will be strong, so they will not fade off easily.
Okay.
Okay.
Is there a limited number of these dyes that can be made?
Yeah, but if we have a different group over here on the benzene ring and we are reacting it with this, we are getting different colors of the dye, but obviously limited.
Okay. And for all, we need the diazonium ion, right?
Yeah.
Okay.
So here we have completed the phenylamine. And in the next class, we are going to start with the chloro or a halogenoyl benzene.
Okay, sir.
Okay, so our next class will be
Sir, is this all one chapter?
No, it's not a one chapter, this phenylamine. Basically, when you look in the book, you will find it all in the nitrogen compound, this thing. But as we have done benzene, so I'm going.
Benzene was the first chapter, right?
Yeah, benzene and the phenol was the first chapter. So actually, I am
Oh.
covering all the things which are related to those aromatic benzene structure.
Yeah.
So that's what I am
All
doing.
of organic.
From all of organic, basically, there are two kinds of compounds over there. The compounds with and their reactions which do not contain benzene, and the compounds which have a benzene.
Okay, sir.
I am just initially covering all the things which are included, which are relevant to a benzene and this aromatic thing, and then we will cover the rest of the one.
Okay. Yeah.
Okay, so we are going to do with the chlorobenzene and the alkyl benzenes in the next class, hopefully.
Okay, sir.
Okay.
So on Sunday? You said we will make up the class, right?
Yeah. And this one
so
is.
do we have class on Sunday?
Right?